Inside a black hole, imagine drifting silently through space. No sound, no motion, just you, suspended in the infinite dark, surrounded by stars that glitter like scattered diamonds on black velvet. Ahead of you, a region so dark that even light can never escape. Scientists call it a black hole, but what would you actually see if you crossed its edge? What would it feel like to approach the most extreme objects in the universe? What happens to your body, your mind, your very existence when you fall into one? Tonight, we'll follow that journey together, slowly, calmly, and as accurately as modern science allows. This is not a journey of fear. It is not a journey of terror. This is a journey of wonder. A journey into the most mysterious objects in the cosmos. A journey that will take you to the very edge of existence and beyond. Let me take you there. Not with fear, not with urgency, with peace, with curiosity, with the quiet awe of someone who is about to witness something extraordinary. Close your eyes if you wish. Breathe deeply. For the purpose of this meditation, imagine yourself as a silent observer, untouched by the immense forces around you. You are safe. You are protected. You are exactly where you need to be. The first glimpse. Ahead of you, the darkness expands. It's not just a shadow. It's not just a patch of empty sky. It's a sphere of absolute black, a perfect circle against the tapestry of stars. This is your first glimpse of the black hole. It's been there all along, hidden in plain sight. But now you see it. Now you understand what it is. The stars around it are bending, to your left and right. The familiar constellations are stretching into arcs of light. The space itself is curved. The geometry of the universe is changing. Straight lines become curves. Parallel lines converge. The familiar rules of Euclidean geometry no longer apply. You're in a new world. A world where the laws of physics are different. A world where the universe is shaped by gravity. This bending of light is called gravitational lensing. Einstein predicted it in 1915. It was confirmed in 1919 during a solar eclipse. The light from distant stars was bent by the sun's gravity. The stars appeared to shift position. It was a dramatic confirmation of general relativity. And near a black hole, gravitational lensing becomes extreme. The black hole bends light so much that it can create multiple images of the same object. It can create Einstein rings, where the light from a distant galaxy is smeared into a ring around the black hole. It can create arcs of distorted light. Watch as the stars begin to bend. They stretch into arcs. They curve around the black hole, forming a halo of distorted light. The light from behind the black hole is focused. It's amplified. It's a cosmic illusion, a trick of gravity. A reminder that the universe is not what it seems, the history hidden in the light. As you watch the bending starlight, imagine how impossible this scene would have seemed to astronomers 200 years ago. In 1783, an English clergyman named John Mitchell wrote a paper suggesting that there could be dark stars so massive that even light could not escape from them. He called them dark stars. It was an extraordinary idea for its time, but it was largely forgotten. It took another century and a half for the concept to re-emerge. In 1915, Albert Einstein published his theory of general relativity. It was a revolution in physics. It showed that gravity is not a force, but a curvature of space-time. Massive objects bend the fabric of the universe, and the more massive the object, the more it bends. A few months later, a German physicist named Karl Schwarzschild found the first exact solution to Einstein's equation. He discovered that a sufficiently massive object would create a region of spacetime where the curvature becomes infinite. He calculated what is now called the Schwarzschild radius. It's the radius at which the escape velocity equals the speed of light. It's the size of the event horizon. It was a mathematical curiosity. Nobody thought such objects could actually exist. For decades, black holes remained theoretical. Physicists like J. Robert Oppenheimer and Hartland Snyder showed that a massive star could collapse into a black hole, but they were still just ideas, mathematical equations on paper. It wasn't until the 1960s that black holes became part of mainstream physics. John Wheeler, the great American physicist, coined the term black hole. He popularized the concept. He made it real. In 1971, the first black hole was discovered, Cygnus X1. It's a stellar mass black hole in our own galaxy. It's about 15 times the mass of our sun. It's about 6,000 light-years away. And it was the first confirmation that black holes are real. They're not just mathematical curiosities. They are out there. They exist. Since then, we've discovered dozens of black holes. We found them by their gravitational effects on nearby stars. We found them by the radiation from their accretion disks. We found them by the gravitational waves they emit when they merge. And in 2019, the Event Horizon Telescope captured the first image of a black hole. It was the shadow of the supermassive black hole in the galaxy M87*. It was a momentous achievement, a direct image of the edge of a black hole, the point of no return, the types of black holes. As you continue your approach, you might wonder what kind of black hole you're falling into. Scientists have identified different types. Each type is different. Each type is fascinating. Each type is a window into the most extreme physics in the universe. Stellar mass black holes are the most common. They are scattered throughout our galaxy. They form when a massive star, at least 10 times more massive than our sun, runs out of fuel. The core collapses. The outer layers explode in a supernova. What's left is a black hole. These black holes are relatively small. Their event horizons are only a few kilometers across, but they are incredibly dense. A teaspoon of material from a stellar mass black hole would weigh billions of tons. It would be heavier than Mount Everest. Supermassive black holes are the giants. They are millions or billions of times more massive than our sun. They sit at the centers of galaxies. Our own Milky Way has a supermassive black hole called Sagittarius A*. It's about 4 million times more massive than our sun. Its event horizon is about 24 million kilometers across. That's about the size of Mercury's orbit, and it's relatively small compared to other supermassive black holes. Some are billions of times more massive than our sun. Their event horizons are larger than our entire solar system. How do supermassive black holes form? We don't know. They are too massive to have formed from a single star. They must have grown by merging with other black holes, or by swallowing enormous amounts of gas and dust. The process is still a mystery. It's one of the biggest questions in astrophysics. Intermediate mass black holes are the rarest. They are between 100 and 100,000 times more massive than our sun. They might form when smaller black holes merge. They might form when a cluster of stars collapses. They are the missing link, the bridge between stellar mass and supermassive black holes, and we're only just starting to find them. Primordial black holes are hypothetical. They might have formed in the first moments after the Big Bang. The universe was incredibly dense. Some regions might have collapsed directly into black holes. These black holes could be any size. They could be as small as a proton. They could be as large as a planet. They could be everywhere. They could be passing through your body right now. We don't know if they exist, but we're looking. The physics of approaching. As you get closer, the gravitational pull becomes more noticeable. Below you, the accretion disk slowly rotates. It's a glowing ring of gas and dust, spiraling inward like water down a drain. The inner edge of the disk is incredibly bright. It's glowing with heat and radiation. The particles are moving at nearly the speed of light. They're colliding. They're heating up. They're releasing energy in the form of X-rays and gamma rays. It's a cosmic lighthouse, a beacon of pure energy. The accretion disk is how black holes feed. As matter spirals into the black hole, it releases gravitational energy. Some of this energy is converted into radiation. Some of it is converted into jets. These jets can stretch for thousands of light years. They can outshine entire galaxies. They're powered by the black hole's rotation. They are a direct link between the black hole and the surrounding universe. The innermost stable circular orbit, or ISCO, is the closest point where matter can stably orbit a black hole. Inside this radius, any orbit becomes unstable and the matter falls in. For a non-rotating black hole, the ISCO is located at 3 times the Schwarzschild radius. For a rotating black hole, it can be much closer. The ISCO determines how much energy can be extracted from the accretion disk. It's a crucial parameter in understanding how black holes interact with their surroundings. The photon sphere is another fascinating region. It's located at 1.5 times the Schwarzschild radius. This is where gravity is so strong that light can orbit the black hole. Photons travel in circles around the black hole, trapped in a perpetual loop. However, these orbits are unstable. Any small perturbation will send the photon either falling into the black hole or escaping. They're a reminder of how powerful gravity can be. The spinning black hole. Most black holes are spinning. They're called Kerr black holes, named after the New Zealand physicist Roy Kerr, who solved the equations in 1963. The rotation of the black hole drags the surrounding spacetime with it. This is called frame dragging. It's a fascinating effect. Imagine space itself as a fluid that's being pulled around by the spinning black hole. Anything that enters this region is dragged along. It's like being caught in a whirlpool. Frame dragging creates an ergosphere. This is a region outside the event horizon where spacetime itself is dragged so strongly that remaining stationary becomes impossible. It's a strange region. Particles can enter the ergosphere and still escape. In fact, you can extract energy from a rotating black hole through a process called the Penrose process. You send a particle into the ergosphere. It splits into two. One falls into the black hole. The other escapes with more energy than it entered. This is how you could theoretically extract energy from a black hole. The rotation of the black hole also affects the accretion disk. The inner edge of the disk can get closer to the black hole, which means more energy can be extracted. The jets that shoot out from the black hole are also powered by the rotation. They are aligned with the spin axis of the black hole. They are a direct link between the black hole's rotation and the surrounding universe. The LIGO detectors have observed the gravitational waves from merging black holes. When two black holes spiral together and merge, they release an enormous amount of energy in the form of gravitational waves. These ripples in spacetime travel across the universe at the speed of light. They were first detected in 2015. It was a historic achievement, a direct confirmation that black hole mergers are real, and they happen all the time. Spaghettification. Before we reach the event horizon, we need to talk about one of the most famous effects of falling into a black hole. Spaghettification. Near a stellar mass black hole, gravity becomes incredibly intense. The gravitational pull on your feet is significantly stronger than the pull on your head. This difference creates tidal forces. They stretch your body. They pull you apart. Your body becomes a stream of atoms, a river of particles, stretching into the void like a piece of spaghetti. Scientists call this process spaghettification. It's one of the most extreme consequences of gravity around supermassive black holes. However, the story is different. The event horizon is so vast that the difference in gravity between your feet and your head is negligible. You could cross the event horizon without immediately noticing these tidal forces. Your body wouldn't stretch. You wouldn't be torn apart, at least not right away. The curvature of spacetime is so gentle that you might not feel anything unusual at all. But the deeper you fall, the more extreme things become. Eventually, even around a supermassive black hole, the tidal forces would overwhelm you. But by then, you'd be far inside the event horizon, far from the point of no return. The event horizon. Ahead of you, the event horizon is getting larger. It's no longer a distant sphere. It's a wall, a boundary, a point of no return. The event horizon is the boundary of the black hole. It's the point where the escape velocity equals the speed of light. Once you cross it, you can't go back. You're committed. You're going all the way. The event horizon is not a physical surface. It's not a wall. It's a mathematical boundary. A place where our understanding of physics breaks down, but crossing it is uneventful. You wouldn't feel anything. You wouldn't notice any change. The event horizon is just a point of no return, a place where the universe outside becomes inaccessible. The event horizon's shadow, the dark region that telescopes image, is actually larger than the event horizon itself. It's about 2.5 times the Schwarzschild radius. The Event Horizon Telescope imaged the shadow of M87* in 2019. It was a historic achievement, the first direct image of a black hole. The shadow is caused by the bending of light around the black hole. It's a direct consequence of general relativity. As you approach the event horizon, something happens to your perception of time. To a distant observer, your clock appears to slow dramatically and never seems to reach the event horizon. From your own perspective, however, time continues normally. You cross the event horizon without noticing. You fall toward the singularity. This is the essence of time dilation. Gravitational redshift. The light around you is changing. The stars that were once bright are now fading. They are becoming redder, dimmer. They are being redshifted. Gravitational redshift is what happens to light as it approaches a black hole. Light loses energy as it climbs out of the black hole's gravitational well. It shifts toward the red end of the spectrum. It gets dimmer. It gets redder. It fades. Eventually, it disappears. The black hole is black because no light can escape. But the light that's falling in changes color before it vanishes. It becomes red. It becomes infrared. It becomes radio. And then it's gone. The universe outside is shrinking. The circle of light is getting smaller. The stars are fading. The light is dimming. And then there's nothing. Just darkness. Crossing the event horizon. You cross the event horizon. The universe outside shrinks to a tiny circle of light. It fades. It becomes a dot. A tiny speck of light, and then it's gone. You're inside. You're committed. You're falling toward the singularity. Inside the event horizon, something fundamental changes. Space and time swap roles. Outside the black hole, you can move freely in space, but time always moves forward. Inside the event horizon, the singularity is no longer a place in space. It's a moment in time. You can't avoid it. You can't move away from it. You can only move toward it. The singularity is your future, and you're falling toward it. Just as you cannot stop moving toward tomorrow, inside the event horizon you cannot stop moving toward the singularity. The coordinates invert. What was a spatial direction becomes a temporal direction. The singularity is not a place. It's a time, and you're heading straight for it. The interior of a black hole is one of the most mysterious regions in physics. We can't see inside. No information can escape. So we have to rely on mathematics, on theory, on imagination. But the mathematics suggests that the interior is not empty. It's full of strange structures. It's full of quantum effects. It's full of possibilities. The interior, where physics breaks down. As you fall deeper, the environment around you becomes more intense. The gravity is stronger. The darkness is deeper. The space is more curved. The laws of physics that we know and understand are breaking down. Classical mechanics, Einstein's relativity, quantum theory, they all start to fail. The gravitational field is so strong that it overpowers everything. Time, space, matter, and energy all behave in ways that defy common sense. Classical physics begins to fail. General relativity predicts one future. Quantum mechanics hints at another. Several modern theories try to bridge the gap. The BKL model, named after Belinsky, Kolitnikov, and Lifshitz, describes the behavior of spacetime near a singularity. It suggests that the singularity is not a simple point. It's a chaotic, oscillating region. The universe near the singularity undergoes a series of violent oscillations. It expands and contracts in different directions. It's a cosmic dance of destruction and creation. It's a region where the fabric of reality itself is torn apart and reassembled. Quantum foam is another concept that comes into play at the smallest scales. At the Planck scale, spacetime is not smooth. It's foamy. It's chaotic. It's constantly bubbling and fluctuating. Particles pop in and out of existence. Spacetime itself is torn and repaired in an endless dance of creation and destruction. Near the singularity, the quantum foam becomes dominant. The smooth continuum of spacetime breaks down. It becomes a froth of quantum fluctuations. The holographic principle is another fascinating idea. It suggests that the information contained in a region of space can be described by a theory on the boundary of that region. In other words, the three-dimensional universe we experience might be a hologram, a projection of two-dimensional information. This is a radical idea, but it's supported by a mathematical framework called AD/CFT correspondence. It's used to study black holes. It's used to study quantum gravity. It's one of the most promising approaches to understanding the interior of a black hole. The singularity. The singularity is the center of the black hole. According to general relativity, the equations predict a singularity, a region where space-time curvature appears to become infinite. Most physicists believe this prediction signals that our current theories have reached their limit, rather than describing physical reality itself. It's not a physical object. It's a sign that something is missing from our equation. But what is the singularity? Is it a real physical object, or is it just a failure of our mathematics? The cosmic censorship hypothesis, proposed by Roger Penrose, suggests that singularities are always hidden behind event horizons. You can't see them. You can't interact with them. They are shielded from the outside universe. It's a way of preserving the predictability of physics. It's a way of saying that the singularity is not a problem, but the cosmic censorship hypothesis is still unproven. It's a conjecture, a speculation, a belief. There might be naked singularities. Singularities that are not hidden behind event horizons. They would be windows into the unknown. They would break the laws of physics. They would revolutionize our understanding of the universe. Penrose diagrams are used to visualize the structure of space-time near a black hole. They show the causal relationships between different regions. They show the event horizon. They show the singularity. They show the universe outside. They're a powerful tool for understanding black holes, and they reveal that the interior of a black hole is a region of space-time that is disconnected from the outside. It's a separate universe, a different reality. AD/CFT correspondence is one of the most important developments in theoretical physics. It's a duality, a relationship between two different theories. It shows that a theory of gravity in a higher dimensional space is equivalent to a theory without gravity on the boundary of that space. It's used to study black holes. It's used to study quantum gravity. It's used to study the interior of a black hole. It's a window into the quantum nature of spacetime. Black hole complementarity is another idea. It suggests that the interior of a black hole and the exterior are complementary descriptions of the same reality. They can't both be true at the same time. They are mutually exclusive, but they are both valid. It's a way of resolving the information paradox. It's a way of saying that the universe is stranger than we can imagine. Beyond this point, our equations fail. General relativity reaches its limit. Quantum mechanics refuses to agree. Somewhere beyond this boundary lies a deeper theory that humanity has not yet discovered. The singularity is not an answer. It's a question that points to the limits of our current understanding, a question that challenges us to go further, to think deeper, to discover more. The information paradox. The information paradox is one of the deepest puzzles in physics. When something falls into a black hole, its information is lost. But quantum mechanics says information cannot be destroyed. This contradiction suggests that our understanding of gravity and quantum mechanics is incomplete. The resolution of this paradox might require a completely new theory of physics. It might require string theory. It might require loop quantum gravity. It might require something we haven't even imagined yet. What happens to information when it falls into a black hole? Does it survive? Does it escape? Does it get destroyed? We don't know, but we're working on it. We're developing new theories, new approaches, new ways of thinking. The holographic principle suggests that information is not lost. It's encoded on the boundary of the black hole. The event horizon stores the information. It's like a cosmic hard drive, a repository of everything that has ever fallen in. The firewall paradox is even stranger. It suggests that the event horizon might be a wall of fire, a region of intense radiation that destroys anything that tries to cross it. This contradicts the idea that crossing the event horizon is uneventful, but it's not clear if firewalls actually exist. They are a theoretical construct, a way of reconciling conflicting theories, but they might be real. And if they are, falling into a black hole would be anything but peaceful. The journey ends. No one has ever returned from beyond the event horizon. From this point onward, everything is theory. Mathematics continues. Observation ends. This is the frontier of human knowledge, the place where science meets philosophy, where physics meets mystery. Our journey ends here, not because anyone has ever returned from inside a black hole, but because this is where science reaches the edge of what it can currently describe. Everything beyond this point is speculation, theory, mathematics, the realm of the unknown. But that's not an ending, it's an invitation to keep asking questions, to keep exploring, to keep pushing the boundaries of what we know, because the universe is still full of mystery. And the greatest discoveries are still waiting to be made. The future of black hole research. What does the future hold for black hole research? The next decade will be transformative. New telescopes are coming. New observatories are being built. New theories are being developed. We're on the brink of a revolution. The Event Horizon Telescope is expanding. It's adding more observatories. It's improving its resolution. It's aiming to image more black holes. It's aiming to make movies of black holes. We might soon see not just images, but videos. We might see the accretion disk swirling. We might see the shadow changing. We might see the black hole in motion. LIGO and Virgo are detecting more gravitational waves. They're finding more black hole mergers. They're exploring the population of black holes in the universe. They're probing the nature of gravity in extreme conditions. They're testing general relativity in ways that were impossible just a decade ago. Future gravitational wave observatories will be even more sensitive. They'll detect mergers of supermassive black holes. They'll detect mergers of intermediate mass black holes. They'll detect mergers of black holes with other objects. They'll open a new window on the universe. The James Webb Space Telescope is observing the early universe. It's searching for supermassive black holes. It's looking for the seeds of these giants. It's trying to understand how they form. It's exploring the relationship between black holes and galaxies. It's revealing the role that black holes play in cosmic evolution. Quantum gravity research is advancing. New theories are being developed. New approaches are being explored. String theory, loop quantum gravity, holographic principle, AD/CFT. These are the ideas that will lead to a deeper understanding of black holes. They are the ideas that will resolve the paradoxes. They are the ideas that will revolutionize our understanding of the universe. Final reflections. Your journey inside a black hole is over, but the journey of your life continues. And now you have a new understanding, a new appreciation for the mysteries that surround us. Black holes are not just objects of destruction. They are objects of creation. They are the architects of the cosmos. They shape galaxies. They influence the evolution of the universe. They are among the most extreme environments we can observe. The universe is vast. It's full of mysteries, full of wonders, full of things we don't understand. And that's okay, because the journey of discovery is what makes life meaningful. The journey of exploration is what makes us human. Every black hole reminds us that nature is stranger than imagination. The deeper we look into the universe, the more we discover how much remains unknown. And perhaps that mystery is the greatest discovery of all. Every image, every gravitational wave, every observation brings us one step closer to understanding what lies beyond the darkest places in the universe. So take this journey with you. Take it into your heart. Take it into your soul. Let it guide you. Let it inspire you. Let it remind you of the wonder of the cosmos. The next time you look up at the night sky, remember what you've learned tonight. Remember the journey you've taken. Remember the awe you felt. The stars are not just distant points of light. They are part of a vast, interconnected cosmos, and we are part of it too. A final message. May your journey through life be as peaceful as your journey through the black hole. May you find peace in the midst of chaos. May you find healing in the midst of pain. May you find yourself in the midst of the unknown. The darkness around you is not empty. It is full of potential, full of possibility, full of everything that ever was and everything that ever will be. It is the source of all things, the origin of existence, the point from which everything emerges and to which everything returns. The silence around you is not empty. It is full of meaning, full of wisdom, full of answers. It is the silence of creation, the silence of eternity, the silence of the universe.